Hello everyone, Professor Dustin here. This video is going to introduce you to Newton's third law. So we all know the quick and dirty definition of Newton's third law. For every action, there is an equal and opposite reaction. So for us, we're going to need to delve a little bit more into this statement. So for instance, action. The word action is what Newton used to describe forces. So we can just say for every force, there is an equal and opposite force associated with that force. Let me just draw the typical picture, which you probably all have seen previously to describe Newton's third law. We have a building, and then a person trying to push on the building. So the person pushes with a force Fp. The building is big, it is not moving, but it does not matter if it's moving or not. The building pushes backwards on the person with the exact same force, Fp, no matter how hard that person is pushing. Okay, so if Fp is the action force, this Fp that the person feels from the building is the opposite reaction force. Okay, fine, but we can be a little bit more careful about where the sources of these forces are to write Newton's third law in a more mathematical language. So I'm going to first specifically name each one of these things, building and person. And then I'm going to differentiate these two forces in the following way. I'm going to call this force the force that the person is acting on the building with. And I'm going to do person building. So that's just my way of saying which direction the force is going in between the person to the building. It doesn't really matter the order here, but that's the convention I usually use. Okay, so how is this force related to that force? Well, it's the same magnitude because we know about Newton's third law, but actually it's different in this notation because now the building is acting on the person. So now I have to write building acting on person. So in a sense, I can also write this as a vector, force of person acting on building. That vector is the opposite, in the opposite direction, that's with the negative sign, of the building acting on the person. So this is the real mathematical statement of Newton's third law, and it includes this exchange of the objects because that's the easiest way to understand Newton's third law from an analytical perspective. So that's the simple picture. Now I want to go into a common misunderstanding of Newton's third law, which is the person standing on the ground and the normal force. Okay, so I've replaced my specific picture with a more mathematical statement of Newton's third law. Fa on B is minus Fb on A. And now I have my person. So if this person has a mass m, we know there is a gravitational force acting downwards on them, Fg. And we also know that that gravitational force is equal to m times g. So we should ask, what are, if any, are there other forces acting on this person? Well, we know this can't be the only force because if it is the only force, the person is then being pulled downwards. It is accelerating downwards, so it can't be the only force on them, just because we know the person is not going through the ground. Typically, we call the force which opposes that, we call that the normal force, Fn. That's a contact force in between the person and the ground. So again, why do we know that normal force is there? Because we know the person is not accelerating. We can just look at them and say the ground is preventing them from being pulled down towards the center of the earth, and so we have the normal force. Okay, a common misconception is the normal force is a Newton's third law pair of Fg. That is, this relationship is satisfied by these two forces, and I want to prove to you that that's not true. That is not why the normal force exists. It's not because of Newton's third law. But I'm going to do that by trying to create the labels, this A-B relationship between all these forces. So that means we have to think a little bit more carefully about what this Fg really is. So Fg is the long-distance interaction between the entire Earth and the person, the mass of the person and the mass of the Earth interacting. So I'm going to just relabel this to try to make that a little bit more clear. I'm going to call this Fg, gravitational long-range interaction, which the Earth acts on the person with. That's because the Earth is pulling downwards on the person. That's why I picked that particular order. Okay, great. So now I want to do the same relationship with the normal force. Well, the normal force is a contact force. I'm going to call the ground here a floor because it doesn't matter if it's the earth ground or a floor ground, something else that's flat that's preventing the person from being driven down into the earth. So if this is a contact force between the person and the floor, so I can write this as FC, contact force, and it should be the floor acting on the person, because the floor is the thing holding the person up. So floor acting on person. Okay, so now I've arranged the letters in the same way that we need them to be arranged for Newton's third law, and we immediately see that they are not related in the same way that Newton's third law action and reaction pairs are supposed to be related to each other, because I can't just switch these and get that. There is a floor, which is an additional part of the system. It's not just the earth acting on the person in the gravitational way and the person acting on the earth in the gravitational way. The normal force is here to prevent the person from accelerating downwards. It is not there because of Newton's third law. We can look at the Newton's third law pair. So for instance, the Newton's third law pair of this guy is going to be minus the force, the gravitational force of the person acting on the earth. This force is a force which I am pulling upwards on the earth. So since the earth is pulling me downwards gravitationally, I am pulling the earth upwards gravitationally in the same exact way with the same force, just opposite in direction. In the same way, there is a force opposite in direction between the person is acting on the floor. So just like the floor is pushing up on me, the person is pushing downwards on the floor in the exact same way. So this might seem like sort of a trivial difference between Newton's third law and Newton's second law, but it actually becomes extremely important because Newton's third law is true. There's always an action and reaction pair regardless of what's going on in the system. It doesn't matter if this thing was accelerating, not accelerating, no matter what. We use Newton's third law to know that the normal force was the same size as Fg, but we could get that wrong if we thought that Newton's third law was the reason the normal force was the same size. So for instance, let's say that I start pushing on this person with an additional force Fp. Somehow, give him a bigger mass, I go over to him and push him on the shoulders, whatever. If that gets bigger, what happens to the normal force? It gets bigger because the person is still not accelerating. So if there's two forces downwards, the normal force gets bigger to compensate. Newton's third law doesn't know anything about that. Newton's third law still says the gravitational force from the person is the same as the gravitational force from the person on the earth. Gravitational force that the floor is acting on the person is the same as the gravitational force the person is acting on the floor. Newton's third law does not change, but Newton's second law tells you that the normal force gets bigger. That's a key difference, and it's something that confuses a lot of students when they come into Physics 1 about how the normal force works. It's understandable, but we just need to be careful about it and know that it's not that Newton's third law tells us how big the normal force is. It's actually Newton's second law. Okay, great. Thank you for watching this video, and I will see you in class.